All right, this is discussion A2, ideal gas law. Okay, so before we can talk about the ideal gas law, we have to talk about what an ideal gas is. So an ideal gas is a gas that will follow the kinetic molecular theory perfectly. Now, what that means is that these gas particles will have fully elastic collisions and it means there will be no intermolecular forces of attraction between the gas particles. Now, these are gases and how they would behave in an ideal world. In the real world, we have real gases. Now, real gases don't follow the postulates of the kinetic molecular theory perfectly. Right? They only have partially elastic collisions. And there are some intermolecular forces between the particles. Now, we can actually make real gases behave like ideal gases under certain conditions. Okay, so we got to think about how we're going to keep the collisions fully elastic and reduce the intermolecular forces. So let's first think about pressure. In the environment, the particles will be farther apart from each other. Now remember, each particle is like a little magnet, and when they get close to each other, they attract each other. And just like with a magnet, if you hold the two pieces of the magnet close together, you'll feel that force of attraction. The farther apart the magnet pieces are from each other, the less you will feel that force of attraction, and so they won't have as much of an influence on each other. So in order to make a real gas behave like an ideal gas, we want to make sure that gas is in a low pressure environment, or at least as low as we can make it. Now let's think about temperature. Now we know that temperature is directly related to the kinetic energy of the particles. Things that are hot move fast, and things that are cold move slow. Right? So again, if the particles are moving toward each other very, very slowly, then that force of attraction between them will have more time to work on them. Right? So the faster they're moving, the smaller the amount of time they'll be in contact with each other, and so the less the influence on their intermolecular forces will be. So we would like to do this at high temperature. So this is something the state wants you to know. A real gas behaves like an ideal gas at low pressure and high temperature. All right, so what is the ideal gas law? Well, here it is. The ideal gas law is PV equals N RT. Well, you may be saying, what the hell does that mean? Well, let me go ahead and define all these terms. P is the pressure. And pressure in this equation must be in atmospheres. So you have to remember that 1 atmosphere is equal to 760 millimeters of mercury, and it's also equal to 101.3 kilopascals. V is the volume, and volume must be in liters. N is the number of moles of gas. R is known as the universal gas constant, or just gas constant. And that has a value of 0.0821. Finally, the temperature, T is the temperature, and of course temperature must be in Kelvin. So the ideal gas law works best at what are known as standard conditions. And we refer to standard conditions with this acronym STP, which stands for standard, temperature, and pressure. So at standard temperature and pressure, the temperature in Kelvin will be 273 or 0 Celsius, and the pressure is 1 atmosphere. So we could also say standard temperature is 0 degrees Celsius, right? Or 760 millimeters of mercury, or 101.3 kilopascals. All right, so let's use the ideal gas law. First problem says determine the temperature of 2.3 moles of gas. So when you see 2.3 moles, write the letter N over it, because you know that the N part of the equation is represented by that 2.3 moles. And that gas is contained in a 1 liter container. Now 1 liter is a volume at 3.00 atmospheres, which is pressure. So as soon as you label these variables, you'll see that one of the variables is the letter N. Now, N only appears in PV equals nRT, right? Not in the combined gas law. So if you see that letter N, you know that you're going to be using the ideal gas law. So let's go ahead and fill in the numbers. So the pressure is 3.00 times the volume, which is 1.00, equals N, which is 2.30, times R, which is 0.0821. Remember, that'll be given to you, times the temperature. So we're going to solve for the temperature, so we'll isolate T. I'm not going to go ahead and teach you that now. But if you don't know how to solve for a variable in an algebraic equation, you need to come and see me about that ASAP. All right, and that's going to equal 15.9. And to determine the unit, it's temperature. Temperature has a unit of Kelvin. All right, next example, I want you to work out all on your own. So take a moment and pause the video and go ahead and do that. All right, so it says calculate the volume. So I already know that volume we can call X. That a 0.450 mole sample, so N is 0.450, of gas will occupy at 265 Kelvin, so 265 Kelvin, and 654 millimeters of mercury. Now, anytime you do a gas law problem, you have to ask yourself if all the numbers are ready to be plugged in or if you've got to tweak them a little bit. Now, since we're going to be using PV equals nRT, temperature needs to be in Kelvin. And as you can see, our temperature value is indeed in Kelvin. And our pressure needs to be in atmospheres. But we have our pressure in millimeters of mercury. So the first thing we're going to have to do is convert into atmospheres. So the conversion factor I will use is 760 millimeters of mercury is equal to 1 atmosphere. And when I punch that into my calculator, I get that that is 0.861 atmospheres. All right, now that we have all our variables, we're going to plug into our equation. That's good. So P is 0.861 times V, which is our variable, equals N, which is 0.450, times R, which is 0.0821, times the temperature, which is 265. 0.45 times 0.0821 times 265 divided by 0.861. Presto changeo. I get my volume is 11.4. Now if you're asking what unit you need, it's volume, so the unit will be in liters. Piece of cake. Okay, so molar volume. This is very, very important. What I'm basically going to do here is give you one more conversion factor to use in stoichiometry. So we know, because of kinetic molecular theory, that 1 mole of any gas at STP will occupy a volume of 22.4 liters. It does not matter what gas you have, whether it's hydrogen, steam, carbon dioxide, whatever. If that gas is in a container at STP, it will occupy a volume of 22.4 liters. So we can use the ideal gas law to prove this. So I want to find out what the volume of 1 mole of gas is at STP. So I'm going to rearrange this equation. It's going to become N RT over P. So N will be 1 because it's 1 mole. R is what R always is. Temperature at STP is 273 divided by the pressure, which is 1 atmosphere. when you punch this into your calculator, you're going to get 22.4 liters. Now, this works for any gas, because if you look at this expression solving for the volume of an ideal gas, none of the factors indicate which gas we're talking about. It will be true for all gases. Now, this becomes really important as a conversion factor, because we can craft an equality that says 1 mole of any gas is equal to 22.4 liters. So if we know a volume of a gas, we can calculate the number of moles. If we know the number of moles of gas, we can calculate its volume. Okay, so because moles are directly related to volume, when we look at a balanced chemical equation, the mole ratio that we see is also a volume ratio. Okay, so here's an example. We have nitrogen with hydrogen making NH3, which is ammonia. All right, so you can't really see it, but there's an imaginary 1 in front of nitrogen. And what this tells me is that for every 1 mole of nitrogen, I'll have 3 moles of hydrogen and 2 moles of ammonia. Now, because of this volume ratio, as long as everything is a gas, I can also say that 1 liter of nitrogen is equal to 3 liters of hydrogen, which is equal to 2 liters of NH3. So it's asking me, if I have 4 liters of nitrogen, how much ammonia will I produce? Well, for every 1 nitrogen, I have 2 ammonias. So if I have 4 liters of nitrogen, that means I'm going to have double the amount of ammonia. So I'll have 8 liters of ammonia. Right, so we can just use the coefficients to determine the ratio and answer the questions. Very simple. All right, so here's a few more examples. I want you to try the first 2 all on your own, and then I'll work out the third one for you. All right, so 3.5 liters of methane. Methane is CH4, like the problem tells you. It's asking how many liters of CO2 will be produced. So just like with the mole ratio, we can use the coefficients. I see that there is 1 liter of CH4 for every 1 liter of CO2. So that is going to produce exactly 3.5 liters of CO2, because 3.5 times 1 divided by 1 is 3.5. So again, 3.5 of those, 3.5 of those. Next question says, how many liters of water will be produced? Well, if I'm starting with 3.5 liters of CH4, I can use the ratio between CH4 and water. So 1 liter of CH4 for every 2 liters of H2O, and that'll produce 7.0 liters of steam. Okay? Or you can just look, if we're starting with 3.5 liters of methane, the ratio is 1 to 2, so there'll be twice as much water, or 7.0 liters. Finally, at the bottom it says, what is the volume of 88 grams of carbon dioxide? Well, remember, we can use that molar volume as a conversion factor in stoichiometry. All right, so if I want to find the volume of a gas, I can find it if I know the number of moles of gas that I have. Now, I can't directly go from grams to volume, but I can convert grams into moles and then moles into volume. Let's go ahead and do that. So 88 grams of carbon dioxide. First thing I'll do is convert to moles by dividing by the molar mass of carbon dioxide. So 44 grams for every 1 mole. Once I have moles of CO2, excuse me, I just had lunch, I can convert moles into volume using that relationship. And when I plug this into my calculator, I get 44.8 liters. I almost said cubic decimeters. Okay. Final example with stoichiometry. It says you got 50 liters of CH4 We're going to react it at standard temperature and pressure. How many grams of water will be produced? So if you're ever given an amount of one substance and asked to find an amount of another substance, you know we're going to need to use the balanced chemical equation and stoichiometry to find our answer. So in any stoichiometry problem, the first step is to convert what you are given into moles, because we can use the balanced equation to relate the number of moles. So there's 22.4 liters of methane in 1 mole of methane. Now that I have moles of methane, I can calculate moles of H2O. So there's 1 mole of methane for every 2 moles of H2O. Now it wants grams of H2O. I have moles of H2O, so I just have to make one final conversion. 1 mole of water is equal to 18.02 grams, and that'll give you your answer. So 50 divided by 22.4 times 2 times 18.02. I get 80.4 grams. All right, so density of a gas problem. So using the molar volume relationship at STP, we can calculate the molar mass of a gas if we know the density of the gas. Right? So we're given the density in grams per liter, and we know that molar mass is grams per mole. So this needs to be the unit of our answer. So the number we're given already has grams in the numerator, so grams is okay. But if I'm going to make it grams over moles, then I have to get rid of the liters. So I know that I'm going to multiply by a fraction that has liters in the numerator. Okay? When I do that, the liters will cancel. But then I have to divide by the number of moles to get my unit of moles down there. So I'm going to multiply by a fraction that has liters on one side of the fraction and moles on the other. So let's go ahead and see how that works. So I'm starting with 3.25 grams per liter. So again, I'm going to multiply that by a quantity that has liters in the numerator and moles in the bottom. Now we do have our conversion factor that says 1 mole of any gas is equal to 22.4 liters. So if we put 22.4 up here and 1 down there, liters will cancel. It'll leave us with a unit of grams per mole. And in this case, the answer is 72.8 grams per mole. So you don't have to be a guru with units like I am, but if you encounter a density of a gas problem, and you will, all you have to do is multiply the density by 22.4 and you will get your answer. Finally, Dalton's law of partial pressures. Dalton's law says that the total pressure of a system will be equal to the sum of the partial pressures of all the gases making up the mixture. Right? This is really, really easy. So here we've got the sum of all the partial pressures. And when you add them all up, they're going to equal the total pressure. So there's a number of ways we could ask you this question. One, we could give you the partial pressures and have you add them up to get the total. Or we could give you the total and all the partial pressures except for one and have you find the unknown partial pressure. It's very, very, very easy, and I'm not ashamed to say that. So example 1 says, what is the total pressure of a mixture of gases if the partial pressures are 1.53, 0.45, and 2.58 atmospheres? So it's asking us, what is the total pressure if the partial pressures are 1.53, 0.45, and 2.58? All you got to do, kids, is add them together. So 1.53 plus 0.45 plus 2.58 equals 4.56. Now, for your units, you have to look at the units of pressure that are used in the problem. Atmospheres, atmospheres, atmospheres. So your pressure is in atmospheres. Next and final example, it says a mixture of neon and argon exerts a total pressure of 2.39 atmospheres. So our total pressure is 2.39. The partial pressure of neon is 1.84. What's the partial pressure of argon? So let's call that X. So we're given two of the values and not the third, so we got to solve for X. So 2.39 minus 1.84, X is going to equal 0.55, and our units are in atmospheres, so 0.55 atmospheres. So make sure you study. I think after watching this video and being in class, you should realize that this is not the most difficult topic all year, and it's a great opportunity for everybody to improve their grade. Anyways, thanks for watching. Bring questions, class.